In this episode, we're going to talk about the spark. Actually, the spark that goes across the spark plug itself and get into some of the nuances. I'm going to fall back on my many decades of experience in racing applications and emissions, drivability of all levels. And my interest, and I'm going to share that interest and hopefully bring your skills up also in that whole concept of what's going across the electrode. And that is going to be a key thing here that we need to have a good understanding of. So let's get going on this. Now we have this running. We're looking at the oscilloscope here. And so I have a snap-on Zeus. And I'm really going to look at just the secondary component. We're not even going to worry about the primary. And what we're going to do is we're going to look at what's going on with the burn line and a kV spike, and then any kind of oscillations from the coil. The design that I have set up here is an old distributed ignition system, a DIS coil pack. I'm running it with a conventional Delco standard HEI ignition module on this little board, and that allows me to have very easy control over it. It's a very simple design, easy to make up. I simply have 12 volts coming into it. I'm using this pulse width modulated frequency generator here to send a signal in that would represent the distributor. I have utilized this tool for decades to check integrity of spark plugs to really have an understanding of what I'm looking at. It's another tool in the arsenal of diagnosis, troubleshooting, and building high performance vehicles. I've always done the tuning portion, run the dynos, so on. That's my area of expertise, and also as an educator I try to convey that information, and that's what this is all about, is conveying that information. So what we have going on right now is I just took a standard off-the-shelf old school AC Delco spark plug, and you can look at this primary line here. We have the firing line, and remember, this is under no load, no cylinder pressure. So we're coming up to a little over 2 kVs. Occasionally it's going to have a little bit of a higher kV that's spiking. And then our milliseconds, we're a little over about 2.25 milliseconds. So that's the length of time that the spark plug is ignited for. So the spark that's going across here, you can see we're currently at 2,500 RPM simulated. So that's the speed we would expect to see the spark, of course. And if you look at the display here on the frequency generator, we're at 21 hertz, and I just went with a 30% duty cycle. So what we want to see here is with the spark itself, the condition and the variance of different spark plugs. Now, since we're not under any pressure, we're just looking at the electrical integrity of the plug itself. I'm going to be switching to a different plug. This will be a long reach spark plug. This first one has a 35 thousandths gap on it, operating at the same RPM. This one has a 40 thousandths gap. It's a deep reach plug. The porcelain sticks out, so it's a hotter heat range. And you can see this has a totally different characteristic. A number of things I think you'd find interesting is, one is from the other plug, we had a little over 2 milliseconds. Here we are at about 1 3/4 milliseconds. So just by simply changing that spark plug out, the characteristics of the plug itself, the slight increase in gap, we did not see a large increase in kVs. But we did see a change, and we also have a lot of noise on the burn line. That is another factor of the transfer of that high plasma energy going across the electrode and not doing it as smoothly as it did on a previous plug. So now I have a plug that has been slightly modified, and I've moved up to 100 thousandths gap. So this one is set up at 100 thousandths, and simply did is I cut a little bit off at the top, so it's not an OEM environment anymore, but I wanted to be able to have this squared, so the ground electrode is still squared, and I simply took off. So I have measured this out at 100 thousandths of an inch, Now this one's giving us yet a different characteristic. So we have, again, a little bit higher kV because of excessive gap, but being both exactly the same spark plugs, one is giving us slightly different burn time. So that characteristic, the push-pull, there's this ratio of the most energy discharged and then the energy that it takes to keep that burn going. And let's get talking about what is actually taking place there. In that burn environment, there's a couple different configurations out there. And this one is a conventional induction style coil. It could be from the old points all the way up to this style. But it's simply we're supplying voltage to system voltage to the coil. We're triggering it, and then we're looking at the discharge. There's also the magneto. I won't cover it in depth, but they both run very similar. And so we're going to talk about current. Even though we're not measuring it, we just know what the theoretical current is. And the theoretical current on this would be around 20 to 60 milliamps of energy, plasma energy, going across the electrode itself. So producing that, so that's the energy potential that's in the coil. That is the amount that can go in and do the work to get the ignition started. If I had a CDI system or a capacitive discharge, think MSD, things of that nature, MSD module, where you're actually firing a bank of capacitors, either singular or multiples. They are actually a much higher energy component. They can range from 100 milliamps all the way up to an amp of current going across because of the ability to charge up a capacitor versus just simply saturating the coil in a conventional manner. But we were worried about what's going on with the spark itself. The reason we have such a concern about the spark itself is we want to think about percentage of misfire and what conditions it's going to be under. Let's talk about the optimum condition for the spark. This would be in any type vehicle. So we'll use a car, truck, light duty. Traveling at 25 to 40 miles an hour under light throttle is the best environment, the easiest for that spark to cross over. Odds are the timing index is correct and going to give you the most amount of cylinder pressure, and in turn still allow you to have the spark fire efficiently, get the burn process going. So that's a good environment, but with outside of that environment, it starts to change drastically. So you might be working on a steady state engine, anything from a little Briggs or Honda, all the way up to a large 12-cylinder, and everything in between. There's lots of different variations. My experience has been a lot on race engines, trying to deal with heavy camming, especially the years before variable phase cam designs. We were stuck with a fixed configuration. So you would have to have the most spark available to keep that engine still stable at idle and yet be able to deal with excessively high RPMs and cylinder pressures. And them are all the factors that kick in to make sure percentage of misfire. And the whole goal with that spark plug, one thing and one thing only, is simple. Percentage of misfire. The goal would be 0. We'd love to see 0 because each time we have non-event, in other words, no combustion, or in some cases even a partial combustion, that is wasted fuel, that's wasted energy, nobody wins. The environment doesn't win, the fuel economy doesn't win, the performance doesn't win, there is no win to it. So thinking about the great depth here with the spark plugs is absolutely key to thinking about that criteria. So what condition is that under? And that's going to dictate an awful lot of what ignition, what spark plug, what gap, and even things like indexing. Okay, there's a thing called cavitation. And cavitation is when the fuel is going across the electrode, and we need to get that to burn properly. And there's things that work for us, and there's things that work against us. So things that can cause a lot of cavitation, where the fuel can't get ignited, would be a short gap, CDI systems or capacitive discharge under light load conditions. They do not like when you don't have cylinder pressure because of the massive amount of energy that's taking place. The worst you'll run into is timing. Timing is one of the worst. So that indexing of the timing is critical. because the spark is relying on the right amount of cylinder pressure for the configuration. So that's key to this whole discussion. Is so the point at which, so think about the bore and the stroke, so the stroke of the engine, the velocity of the piston coming up, remember it's got to get maximum velocity halfway up, it stops at the top and goes back down. We got to catch a certain point. They have maximum cylinder pressure about 18 to 23 degrees after top dead center. Your number may vary simply because of the stroke of the engine and a couple other criteria, but that is pretty much a good rule of thumb. So think about getting maximum cylinder pressure. Think about bicycle. If you're pushing down on that pedal, there's a magic point at which the right correct leverage angle is there, and you're going to get maximum push. The combustion process is quick and it's crazy powerful. So let's go on and think about things that will actually help keep that spark there doing what it's supposed to do. High compression is number one. However that is achieved, either mechanical, cam phasing, artificial, turbocharged, supercharged, all of them are going to keep them gases around the spark plug. The next one is the vehicle under heavy load. Heavy load, simply by its nature, is going to have higher cylinder pressure. Even though the frequency of occurrence is greater, it's still going to have that cylinder pressure around there. And then, of course, the last but not least, but a tried and true method is simply multiple discharge. MSD, a few others have gone with that. There's even some of the OEMs, like Ford, has got some multiple discharge systems. So under the poor conditions, idle is an example. In the case of emission engines, excessive EGR, they rely on it multiple strikes. You have multiple times that. But none of this is a panacea. The whole thing is to figure out how to ignite that fuel that is sitting across that electrode and make sure there's enough pressure around it so we can ignite it and get it going. The process of getting it going is something that's still been up for debate. There's a number of different sciences on it, and there's three different theories. They get debated around quite a lot, been getting debated for a lot of years. I'm sure science is kind of established. I mean, it's just something kind of nice to know. There's three theories, and one is going to be simply, think about a match. You're just simply, the spark, the plasma that's coming across there is hot enough, it ignites the fuel molecules, and flame propagation occurs. Number two is kind of called the ping pong theory. As the electrons come across there at this incredible speed, they bump into the hydrocarbon molecules, bounce them around, and simply the friction of that starts, the flame kernel gets the process going. Last is going to be the bullet theory, and that's the high velocity initial process of the spark jumping across there and going through, and not necessarily bouncing anything, just simply as it strikes each one of the molecules of fuel, it ignites. So that's your three theories. You tell me which one that you like the best. Now let's talk about what's going on with the plug itself. The plug itself has got a lot of characteristics that we have to concern ourselves with. First off, the heat range, all that's a specification. But what's the condition of the plug itself? And we're going to, for the most part, deal with talking about new plugs. I do have one example of an older spark plug, and that's going to be a situation here that it's energy leakage. So remember, we're measuring voltage on the lab scope itself. And I mean, I go back to the old oscilloscopes, the old Sun and Allen days. So I have a chance to see a lot of waveform patterns over the years. But the one thing we've never really been able to do is to truly measure the current that's going across. So if we want to think about the amount of work, the voltage is a key component, but it's not the end all. So let's go ahead and we're going to switch over to a plug that's got some problems. Okay, this plug's got some problems. It's basically got some fouling on it. So it was out of an engine that was in kind of sorry shape, so it's already in pretty bad. You can see our kV value is a little bit lower. We also got a lot of ringing. It's having trouble, and what that means is going on here is we have leakage. What's happening is instead of it ionizing across the gap, some of it's leaking back down through the porcelain, and you're losing a percentage. Think voltage drop. So in this case here, we do have voltage drop. It's unfolding here, and that is an indication. So if you're going to go into the whole analysis, and I can do that in a future video, going back to the sun days, the snap-on days, and to current, and how to read the waveform. But for right now, let's just talk about the core, the base level. And the base level is simply if we have something sucking off a certain amount of energy, there's going to be a power factor to that coil, down the spark plug wire, and ultimately to the plug itself. How much of the energy is capable of getting there and doing the job it's supposed to do. And that's the part I wish we could measure, but there's really not any affordable equipment to measure the current. But as you can see here, we have that leakage off that condition of that spark plug itself. So that's kind of spark plug you really don't want to see. Let's go on and we'll add a couple others to the equation. We've got some Bosch Platinum, and that Bosch Platinum plug is very precise. That hard, rare material there simply is incredible conductor. It keeps it very precise. The spark is not dancing around. So the uniformity of that plug firing is and is also much more narrow, very focused. Kind of think about a focused beam. And that focused beam of plasma is going to be able to strike and be more, hence the word focused, able to more easily ignite. So that's one of the positives of these rare material ones. This other plug here, this is NG plug, and it is the V-groove. And the V-groove, it's just a different way of going about it. It's a copper style, but so it's a little bit more exotic material. But they're relying on it so you get kind of the dancing effect of the spark going from one back and forth versus just kind of random. So they're trying to realize, as you get burned on one side, and usually it flips. That's just the way it. Now we're going to get really talking about the real world here, and that has to do with spark lag. So right now I'm at 25 milliseconds. I've got a burn line of a little bit over. So it's a little bit over 2 milliseconds. That means the crank is going to turn around 30 degrees of crankshaft rotation from the very beginning of the spark to when it extinguishes. So think about that. Engine at 2,500 RPMs, that's not excessive, is going to turn 30 degrees of travel in that period of time. So that is before we can even achieve the flame kernel. We've got somewhere in that time period, that 30 degrees of rotation across this burn line, we now have got what we call adequate ignition. And so I grabbed one out of the corn bin here, and we have a flame kernel. So think about 100 thousandths. When you have a ball of fire around a spark plug electrode rated at 100 thousandths of an inch, at that point, it is figured in as having secured combustion. If you're lighting a stove, getting a campfire going, you need a big enough fire to get it to propagate. Of course, there's all the turbulence, other factors, but simply use that as a mental exercise here. Is we need around 100 thousandths diameter of fire, of this flame propagation, to actually do an adequate job. And that can take up to about half as a rule of thumb. Now, there's a lot of rules of thumb with this stuff. But you might have another 15 to 20 degrees of crankshaft rotation. So if we're at 30, and we'll just make it simple. We'll go to 45. We have 45 degrees of travel before you actually start getting the rapid expansion of the gases from the flame from propagating across. So in at 2,500, you go to 5,000, you double this whole entire game. So think about when that cylinder ignition event is going to occur, then think about how it has to roll back to the point where it actually expands. Pretty complicated science. As we're getting into the new modern coil on plug with direct injection and so on, this stuff gets easier because they're using all software. They're using knock sensors to roll it right up against the maximum point. So that's great. I love that technology, but you may not have it. Race application, industrial application, all that. We need to have an understanding in all facets. So if you learn from old school, the new stuff is easy. And that's what I found. I understand how it works. Once you understand how it works, going forward is real easy in comparison to just strictly looking at all the advanced technology, but never understanding exactly how it works. Okay, in this next section here, we're going to start talking about the effects of turbulence into the cylinder. That is really what this is all about. I mean, the turbulence, part of the compression that we have, different engine configurations. And we'll talk about spark plug indexing. It's a topic that many people bring up. Some people think it makes a big difference, some make a little difference. But overall, it makes a difference. And that's what we want to think about. It does make a difference. So let's go ahead and get her going here. So I took my wide gapped spark plug just to illustrate, make this a little simpler. And the first thing we're going to do is we're going to take just some regulated, there's not about 20 pounds of pressure here, and I'm only going to let a little go through. So watch the burn line and look at the spark. So at that point there, the ground electrode is facing away from the turbulence, where the high velocity air is coming in based on whatever type of induction system that you have. But when that intake valve opens, it rushes into the cylinder. That momentum of the air is still there, even though the valve is long since been closed. There's momentum, there's turbulence. The piston went down, the piston came up, and there's movement within that cylinder, some great, some very little, but it's going to have an effect on the spark quality and ability to have ignition itself. Now what we're going to do is turn the plug the opposite way. Now that we have the plug turned the opposite way, I want you to take careful note here of when we have that turbulence unfolding. Remember, this is super exaggerated from what you would have in your engine. Well, unless you had like an exhaust valve burnt, then it's not. But you can see here that I'm going into it, it has a different ground path. And that different ground path, you can see we're not, even with the same amount of air, the severity is not as great. And I didn't cherry pick with the plug. It's just easier to demonstrate with a large gap than it would with a smaller gap. So just be aware that that's how it works. And so plug indexing you might find to be benefit in your application. Depending on what you want to do and how you're doing it, this could be a positive or a negative. Let's go ahead and we'll talk about a couple different configurations. I'm showing a conventional Hemi or semi-spherical combustion chamber, and you can see where the intake valve is here, and so we just assume that we're going to have a flow coming in. That momentum is going to have some inertia to it. There's a lot of factors, but in the environment that a hemispherical engine is, it's pretty mundane for the spark plug. That's one of these. You just don't have the turbulence. You just want to get it packed tight, and they actually fire easier. The next one is going to be kind of an exotic, but man, that really works. Is these twin spark plugs. You got 2 chances at it. So you're going to have the luck. It just you double your percentage. So reducing that misfire is going to be the key to it. So that is that's an engineering thing, not something you're going to have any control over. Just want to illustrate the difference. So things that we covered in this section here. So we talked about the spark plug materials. We talked about the types of ignition systems and their characteristics. We talked about the pressure around the cylinder or in the cylinder affecting the spark plug. And then last but not least, we talked about the turbulence that are in there. Them are all factors affecting that spark plug. So when you think about your troubleshooting, if it's that little Briggs & Stratton, a big industrial engine, a top fuel dragster, or it's an emission job, whatever it is, you're trying to figure out a P0300 code. Think about what the world at which that spark plug lives in. So I truly appreciate your time. Make sure you subscribe and comment, and have a wonderful day.